could you tell us about your background briefly?
Good. I'm a senior scientist with IBM in the General Products Division laboratories at Monterey and Cottle Road. My work has been from earliest childhood in the study of the conversion of energy inside of crystals. I started at the age of 7 on the exploration of bioluminescence of firefly, the light of the firefly, and by 11 I was synthesizing the chemical that made the firefly glow, the 3-amino phthalate 1,4-dione. It's a chemical analog to that which is in the firefly, and from that point on I've focused my life on the study of luminescence, the conversion of energy in crystals. The materials that are in your color television, that are fluorescent lamps, and built my own corporation in this, and then developed for IBM the magnetic disk coding memory system, which now IBM uses throughout the world in their disk memories. I've developed the coding. We hold the basic patents for this material, and I've been into the field of material science all of my life. For the past 20 years, since 1960, I've developed a skill in optical microscopy because I wanted to study liquid crystal systems. I said there will be a very important new discoveries made in liquid crystals. These will be useful in watches, display devices, and I proceeded to develop these materials for IBM. With that, I put together probably the most complete optical microscopic gear, about almost $250,000 in optical microscopes. And this brings us to the present point where I was contacted in April by Mr. Jim Della Tosa, and they told me about this unusual sighting on, in Switzerland by Mr. Myers. I've had a rather negative feeling towards UFOs because I said, unless I have something physical that I can get my hands on, just reported sightings and things like that have no interest to me. And from a human interest standpoint, I said, fine, I'll see what I can do to investigate these specimens that were left by these contacts. And so Mr. Della Tosa contacted Mr. Stevens, and he wrote to me the letter and sent me 3 specimens, a crystal. In fact, this was the first specimen that it was sent to me, a quartz citrine specimen, a bit of fragments from an asteroid, and a piece of metal that they claim came from the space vehicle.
And did you analyze all?
Yes, I did. Then I took these specimens, and before I analyzed them or touched them, I have been working with many people who have a high degree of sensitivity, called your psychic powers. So I had them psychometrized first by a professional, Mrs. Sheila Brown, and then I took a computer programmer who I've been working with, Bob Swanson, and had him investigated. And when I do that, I use this quartz sphere as a focusing device. I just, piezoelectric, I pump energy into it, apply a field to the person I work with, and then the person then gives me their impressions. And I've taken that and put it onto tape, videotape. Before I touched the specimens or did any technical and scientific work, I did the investigation of the metal specimen, and much to my surprise, much of what was given in psychometry was borne out by what was spoken of by Bob Swanson. If you want now, I can show you some of the results that we got with the first specimen that was given to us.
Yes, please.
I have this in this little notebook here. This is the letter that was sent to me by Mr. Wendell Stevens, and I indexed each of the type of specimens with a code number. The photomicrograph under low power is shown here of the specimen, and I've taken and given to each discrete area a index number. Magnification is 8 diameters. The physical specimen was almost identical in dimension to what you are seeing here. Very much alike. This is another specimen. Now, we took under polarized light and examined. This is under just reflected light coming in at an oblique angle. Very interesting thing is a goldish area here, there's silvery, but also these peculiar flow lines coming. I then went and used Nomarski interference contrast microscopy, and we came across now crystalline patterns, which are in here. And again, you notice these flow lines, like a material being melted and pulled out like taffy. This is very unusual to see a metal specimen exhibiting these type of both composite crystalline patterns and metallic luster of a piece of metal. But even more interesting, I start to go now into this area here, then using what we call polarized light. We polarize light and going to a little higher magnification, only 63 diameters. We got to highly birefringent areas. These colors are caused by the optical rotation of your light, giving you these intense colors, which we call birefringence. And circular areas, little deposits of crystalline formations in these circular areas. Now, I decided to go, I saw that it was what I call a composite, means it is composed of a varying grouping of materials. I had to go to a discrete form of analysis, not just general analysis or even cutting a piece out, but I had to leave the specimen alone and study it piece by piece. And that was done with the Hitachi scanning electron microscope. I work now with an associate of mine, Dr. Wee, and this is now a scanning electron micrograph of A1 area, and this is A2. This is 500 diameters. This is now this area here blown up to 2,000 diameters. This is a field emission microscope, so one gets then very, very high degree of depth of field. The specimen was not touched, which means I did no gold plating, no metallization of the surface, so it was left alone. And what excited me was the tremendous ability to get a depth of field in the specimen without ion burning. In other words, the electron beam did not accumulate. These surfaces acted as conductors here and gave us then a very sharp, clear delineation of the picture. Normally you have to take and cover this with gold, to get a sharp picture. We then took, at this magnification, 2000x, and did a elemental analysis by X-rays. This is the attachment to the Hitachi microscope, and this is the result of our analysis. It is a host of materials, literally the entire cross-section of elements. In this crystalline area, the predominant element was silicon, which is this band here, and iron, and there was a secondary band of sulfur, which is right here. These were very, very intense bands, and we did not attempt to go through the analysis of all the other particular lines that were present. We just took the three main ones and we stopped there. We moved to another section, and I will come back here to this area. And now we were going into this plane right in this region, and we found evidence of what looks like mechanical manipulation. One sees now discrete marks in a diagonal form in this direction and marks in this direction. But what is exciting, it looks like it's been plowed. In other words, a pressure, and there is a scarfing on either side. And you see the regular spacings of these. And I was just working a space group out here, and they're very regular. We did an analysis of this area here. Now we're at 500 diameters. The elements that we found were totally surprising. The major element, which is shown here, was the rare earth metal thulmium, Thulium. It was totally unexpected, with a very small trace down here of bromine. This minute bump down here was a combination of argon and silver. Now, the remarkable thing that we noticed was that, yes, we got this band here. This was the only one that matched in the spectral analysis in the computer, but the secondary bands that are connected with it were not present, which meant that it was a very pure metal, but the secondary emissions were not present. We went on to the third area, very silvery in color. No structure compared to what you saw here.
Yes.
Very little detail. 500, if we blew it, it was very dense, very compact. And sure enough, that silvery color was silver, Ag. Pure silver, again, very pure, but nowhere near as pure as the thulmium. Secondary bands were here, and one minute trace of copper. So now we've seen silicon, iron, thulmium, silver, and copper, all in a specimen about this big. Most interesting thing came, we went back and took another look at the crystalline area. I wanted to explore deeper, and we adjusted the focus. This is 2000x, and sure enough, in this area came a hexagonal shaped crystalline pattern. You can see each of the faces here clearly. When one looks more closely, we can penetrate, and we see the receding faces in back of this crystal plane. This shows extreme penetrating power for your electrons to bring out this detail. From a microscopy standpoint, it is very exciting to get this type of detail. We then went to the tip of the crystal, and that tip is personified by this edge right here. And here you can see it 40x, very low power. This tip and kind of debris present on here. We analyzed this tip, and we found to our surprise that it is essentially aluminum. So we have aluminum, trace of silicon, again, chlorine, and a bromine. This is where we stopped, and the next day I was going to share this results with one of the people from NASA, Ames Research Center, a Dr. Richard F. Haynes. I had put the specimen away in this plastic envelope, which I have here, and when I took the envelope out of my pocket and went to share it with him, the specimen was no longer present. It had disappeared. I retraced my steps, checked with Dr. Wee, my wife, everything. I had two of the specimens fitted together this way. There were three of them all together in my pocket. And at this time, I no longer had any additional this specimen.
Wow. Yes. What do you think of this phenomenon?
I called Mr. Stevens, and he said, I'm not surprised. He said, this has happened before. And I've seen many strange and wonderful things throughout my lifetime, and I accepted this as reality, even though it disturbed me. I wanted to complete this work into doing X-ray and additional studies, and I called him, can you give me additional samples to work with? I want to complete now the work. My interest was piqued because I saw things that really intrigued me. So he said, fine, and he came in person and delivered now the specimens that you see on the table here.
Before we go to the another specimen, what is your opinion about that disappeared metal, or materials, whatever it is? Is it normal? Normally, is it exist
Well,
on the earth, on our world, or?
I've had this happen before to me, and when I've worked with crystals like this,
Yes.
I'd work with a crystal, study it, as I have over the last 10 years, and suddenly the next day I won't go to reach for it and it will be gone. It will have disappeared. I first accused myself of being negligent and not paying attention. And finally I just put it aside. I said, if it happens, it happens. I won't let it bother me. I don't know how to explain it. I have no way of giving any rational explanation. And at this moment I must categorize it as a mystery. I've had it happen too many times to me. If I'm not to work on something, or if something is not right, it will disappear on me, even my own work.
I see. And what is your result of
Of this here?
Of this material?
Right now,
Yes.
I could not explain the type of material that I have and its discreteness by any known combination of materials. I could not put it together myself as a scientist. To get a combination of thorium, silver, and silicon in discrete areas. Yes, if I were to melt it together, I would see the evidence of all of it, but their discreteness is what intrigues me. Do you understand what I'm saying? Because you see, if I were to take these combinations and put it into a furnace, melt it, then pour it out and pull a little ingot, I would see all of these elements present there in any one area. But I don't. I see this discrete bits of material. Now, it can only happen by some form of a cold fusion process where you have the elements present and you fuse them together so they still maintain their identity, but they interpenetrate into one another.
So in other words, do you think there is a possibility to find naturally on this earth we can
Like
find?
this. I'm going to look. I'm intrigued now. This is the type of thing I enjoy doing and dealing with, but it's also a challenge because I showed it to one of my friends who was a metallurgist, and he shook his head. He said, I don't see how it can be put together. And that's the way we are right now. And I think it's important that those of us who are in the scientific world sit down and do some serious study on these things instead of putting it off as figments of people's imagination. I respect Mr. Stevens and the people I have met. I respect their integrity. I'm doing this with no attempt, no desire for any form of remuneration. I want to know, I want to see. And that's the only reason that I'm digging into it. But if it's be a business or it's part of a corporation, I'm doing this independent of IBM. I want to know what these specimens. Now, these were examined previously by a scientist in Switzerland.
Yes.
And he had analysis of them. Now, what the claims are on these are rather interesting. The scientist is Dr. Walter W. Walkers in Switzerland, and what he did, he took these specimens that were given to him, mounted them in plastic, and then polished this surface to get a polished surface. So each one of these represent different stages of the development of the metal that is used in the skin of a spaceship. So these represent 1, 2, 3 stages of the state of metal used in the skin of this spaceship. Now, number 1, which is this, they claim, contains the same state of metal as number 4, which is this one here. Except number 1 had been exposed to the aura of the human body for a long period of time by being carried in the pocket. And it had disintegrated to a certain degree, and this has still held its form. As you see, it's in fragments of powder, very small. This is still somewhat black or metallic looking, and when you polish it, you can see the metallic luster of it.
Could you show it to the
I
camera?
will show it to you now. This is number 4, and here we are. It's black in appearance. Can you see it clearly? Has no metallic luster or sheen to it. This is a preliminary stage to the development of the others. Now, according to Dr. Walker, this metal contains lead, and the majority of it is silver with a trace of copper, some bismuth, and calcium. Now, that's all. But I want to, and I've studied now, and I've done the photomicrography for you of this, of what is the individual discrete nature to this. And when we get it under the microscope, you can see the way this thing is fitted together. Now, what I found, which is most interesting, is that where we start with this number 1 specimen, and we look at one of these little specks, we'll find a and copper. Now, I will be analyzing this, but not from an overall standpoint, but for these discrete elements in there. And then I can then put a theory together of how this thing is brought into being. Now, these are discrete steps, so we'll go from 1 to 4. Now, this is the metal as it is in this stage. This is the specimen that is put into a piece of plastic, polished down, and I will examine this under the microscope. And you will see this from the motion pictures through the microscope. There shows the same threads of the white birefringent material and the metal flowing in together, becoming much more intimately bonded. Now we go to the next one, which is number 5, more highly metallic. Now, if I get it right in the light, you can see the glistening sheen to it. This is a silvery metal. Now we can come to the pictures that I've taken of this. This is the metal here. We get the specimen out. All right. Here's the tip of it. It's grayish silvery color, whitish crystalline deposits, brownish red. This is more than likely copper because of the color. This is more than likely a silver. This is more than likely then a calcium deposit from the analysis now that I'm drawing from Dr. Walker's. I will go into more precise analysis of each of these and to see then how the thing is brought together. Now, do you notice the discrete nature of these materials? Now, this is one side. Now we take the specimen and turn it over on the other side, and we get this type of detailing. Again, these whitish deposits that I'm talking about, and the dark metallic-like luster, and then these reddish deposits. A little better view of that is shown here, reddish, white, and dark metallic. As you look at this, as you can see with your eyes, it does not look like something that is put into a furnace and melted. It looks discrete. individual.
Right.
There's another picture of the same tape with the different forms of illumination bringing out these deposits. Now the last specimen is in their statement, the final goldish silvery metal.
Mm-hmm.
Now this is truly metallic. It does not show any of these whitish materials, and it has been analyzed by Dr. Walkers with what we call Knoop hardness testing, which is a diamond indenter, and they squeezed it into the surface.
Mm-hmm.
And the photomicrographs, you will see this impression squeezed into the surface, showing that it is metallic. It has all the property of metals. Now, the people who delivered these specimens claim that this is done by a cold fusion process in vacuum and not using heat. Now, we, with any technology that I know of, could not achieve this on this Earth's plane. And it's very exciting when you can get specimens like that and have the opportunity of looking at and examining them.
So in another word, could I say this material is extraterrestrial?
It doesn't look like anything that we've made here. At this moment, I would feel very much inclined to accept what was given to me as being true.
I see. Now what is this?
That is citrine.
Yes.
That is a SiO2, silicon dioxide, and this is a single crystal. Now, the people who delivered this claim that this came from the planet Alcyon in the Pleiades chain.
Mm-hmm.
The extraterrestrials who deliver this say that they are from the Pleiades complex, which are the 7 sisters, and that this particular specimen came from the planet Alcyon. And I find in truth that there is a planet Alcyon mentioned in the Encyclopedia Britannica.
Mm-hmm.
Now, I have used this crystal in focusing with another crystal that I have, which is a amethyst crystal, natural, with a quartz overlay, and bring these into opposition with one another, and one gets then very strong energy fields generated between these two. Working with a sensitive, they tell me that this type of crystal will have very powerful healing properties, which means to balance the etheric body of an individual. I will test this out now and see what can be done with this. I want to wire this with various type of recording devices to see what type of characteristic frequency this will have in comparison to other crystals.
Mm-hmm.
I'm just in the preliminary investigation of a crystal like this. One other one, which I enjoyed very much, is this sample here. We should get this on a white background. Is of quartz with a small termination of amethyst color.
Mm-hmm.
This came from the same source. So it gives you a beautiful crystal specimen.
Mm-hmm.
I'll have a chance to study it. I'll see what can be learned about it. But these are the things that I want to dig into, is to find out what is there. Now, I was just given by Mr. Stevens a specimen just before we got on the air, which he tells me is a bit of plastic that is used in a control device by these space people.
Mm-hmm.
I don't know what it is. I just received it. It has no odor to it. It is quite brittle and quite hard. It will be interesting to find out now what this is. But if this is the case, here is part of one of the control devices that a space individual wears on their body.
It's very interesting. So, as a result of your whole experiment, what is your opinion about those materials?
I want to look. I must go much deeper. I have to do X-ray work, further electron microscopy, and if in my own mind I am convinced that everything I see here is true, I will publish on it.
I see.
I'll try to publish it in Nature and let the chips fall where they may. Because I think we must start working on a dedicated basis to look at these things and find out why we are given these grouping of specimens. I respect the people I've met so far, their integrity, their willingness to work. Mr. Della Tosa in his work on photography, and Mr. Stevens, the way he has done his best to give me specimens. We have all done this for one thing, to serve and to find out what truth there is to this. I understand you have visited the individual, Mr. Myers, who has been given these specimens. What is your feeling about him?
Well, he's an honest man, and you know, he's living very simple way.
Yes,
And
it's on additional pieces of that. I want to go in much more critically into doing what I call iron milling. I want to mill the surface away, step by step, atom by atom, and see how the composition is put together. You see, it's not in just gross examination, it's looking into small details, and then you have to visualize how the thing is formed and put together. And this is where the skill of a microscopist and a material scientist has to come in. You have to not only analyze it, because if you analyze it, you can pass it off. You can say, well, this is silver solder. And it's not the case. There are structures that I would not find present in silver solder.
is there any way to get the proof that these materials originated in extraterrestrial planet?
You have to find a combination of matter that you could not duplicate on this earth plane. You have to prove it by almost a backhanded way. And I've already checked out these things for magnetic sensitivity, non-magnetic. None of them show any magnetic properties. I've looked at them with ultraviolet light. I've seen nothing with ultraviolet radiation in fluorescence. I'm now starting the process of near-infrared microscopy, looking at them with near-infrared and doing spectrophotometry of this. I'm going to look now for a combination of organic, inorganic. And if I find anything of an organic nature, yes, then I'll say it's highly unusual.
I see. So
But it's, I'm just in the, you're seeing the early stages of a serious attempt to find truth in this.
I see.
That's
Well,
why I've enjoyed being with you.
thank you very much.
My pleasure.
That's a very nice interview. Well,
Come on. Was given to me in the preparation of the metal for a spacecraft. We're looking at the object now, which has been mounted and polished under cross-field polarized light using a 250-watt cesium iodide light source. There is birefringent areas in the middle of the picture, and as we rotate the analyzer, we'll see the specimen of the metal appear here. It is rather complete in the sense that there are no precise differences in grain boundaries. There are occlusions in the material which are quite birefringent, especially around the edge of the metal. As one rotates the analyzer now, one can see these strongly birefringent areas. has a thin skin of a crystalline-like material, highly birefringent, white as one can see here, and the metal itself has minute specks of also birefringent material in it. These must now be analyzed by the scanning electron microscope. We're dealing with a rather low magnification. In this case, it is the 6.3 X-pole, so we're about 100 diameters. We'll go now to higher magnification. We're now at 1,600 diameter magnification, and now a whole new world appears in this specimen under polarized light, cross field. There are structures within structures that one sees, very, very unusual, and which now bear investigation. At lower magnifications and without oil, one just sees a metallic surface. Now one sees a structure which is composed of various type of interlacing areas. By the use of television, we can get a isodensitric value showing these areas, and as I rotate the analyzer, we overload the Vidicon to see these areas. Now we're coming in again. Look at the center of the screen and you will see these areas start to evolve. Here they are now by use of the Vidicon tube. Here they are being brought out. These are structures within structures. This is very exciting, very interesting, and bears looking into. This is the polished specimen. We're at crossfield. We're using the 251 xenon cesium iodide source. We go to higher magnification yet, and higher yet. We're now at over 2,500, and one can see these birefringent structures. Very exciting, and we must go now to the scanning electron microscope. This is very unusual for a metal to have these birefringent areas. A metal normally will not exhibit this. The birefringent areas are the white portions and the deep bluish areas that we're seeing on the color screen. I'll expand this. Now we'll move on to other specimens. We'll scan for a moment. The edge again. This is the edge. It's the highest magnification one can go now in the optical system. And from here we must now go to the scanning electron microscope. Okay, we will stop here. Unmounted as received by me. It is silvery, as you can see, in color. It looks like it has been melted. This is the raw specimen which was mounted in plastic, lapped and polished in Switzerland. And now you can see this metal in its pristine state. It is remarkable. We will now illuminate it by oblique illumination. It has many facets of color to it. Taking out the analyzer to bring out some more of the metallic sheen and luster to it. And as one goes to higher magnifications on this specimen, one will see other fascinating details. This type of research takes many hours to fully exemplify. We'll look at the backside of this specimen now. This is the backside of the specimen, and under cross-field polarized light, one does see these white crystalline birefringent deposits. The luminous area to the right is just a reflective glare from the light source, as one can see here, but we're dealing now with polarized light, and there is this area illuminated. One side is highly metallic, the other has some forms of crystalline occlusions attached to it. I'm using no objective lens in the Zeiss Ultrafo 3B, and am using what is called the pH position, bringing in a Bertrand lens, and I'm focusing with the Bertrand lens to bring out the details. Gives me the lowest power in the microscope, so I can bring the specimen totally into the field of view that one is seeing here. It's a very small but highly convoluted specimen, so it takes many forms of light. The cesium iodide, 2 incandescent bulbs on the left and the right-hand side. Now we'll move to a higher level of magnification of this and see what we will find. We're looking at this specimen now with Nomarski interference contrast. The objective is a 8x pole, so we're between 80 and 120 diameters magnification. Under interference contrast, one sees now a vein of highly birefringent material running through the specimen we did not see before. What I'm pointing out is that to see the details in this specimen requires an extensive use of all the tools of microscopy. Now we can see banded structures in the center of the field, like fold lines as one would encounter in lava-like flows. The material looks like it has been extended in a flow process, but it does not show what one would see in a furnace from extensive heating. The remark has been made that this specimen was made by a cold flow process. And this seems to be the case here, because one finds areas of structure which are highly birefringent, as one sees in here, very distinct lines. Here is a complete pattern of material flowing in and precisely stopping. Here one can see a better detailing of this. It's like a material has been kneaded and rolled over and flowed together. Here's another band. There you can see a good view of the structure now on the surface. I'm putting the analyzer in, rotating it. We'll go now from the quartz iodide lamp that we're using here, 100 watt to a 250 watt cesium iodide. Much more detail is evident, and one gets better penetration of the light into the sample. Coming back, you're conscious of it, but now we can clearly see it. I will examine this specimen later on with infrared and ultraviolet microscopy to look for further detailing. This is pure exploration, because one does not know what one is dealing with at this time. We'll go to one more level of magnification. We'll go to a higher magnification in this particular area and see what we will see. Here is the same area now at 160 diameters, and one can clearly see distinct areas in the specimen. If one were to use gross examination of the specimen, one would lose the significance of these discrete areas. In the analysis we will do now, we will take each one of these areas and examine them in detail. Go to a higher level light source. Suddenly these things come out in sparkling detail. Reducing the field diaphragm. Adjusting the aperture diaphragm. There's the edge of the diaphragm. Quite difficult in area. We'll move around a bit. And little tiny crystallites. These banding are fascinating. Here it is here. There we are. What I am trying to visualize is how this thing is put together. There are discrete bands of material you saw in the lower part, and they look like they've been manipulated instead of made by nature. With this now, we will conclude with this specimen. This is sample number 6, mounted in a whitish plastic, which they were used in the final development of the spacecraft. The indentation marks are Vickers indentation hardness measurements that were made before in this specimen. We will see these as we go up in magnification. To give you an idea of the size of the specimen, I will put a marker for identification and measurement purposes. We have now in the field of view a metric scale. Each line is 1 millimeter in division. So we see that this specimen is 4 millimeters across, and about the equivalent size in the other dimension. Let us go now to a higher magnification and observe what this specimen looks like. Using now a 4x objective giving around 50 some-odd diameters magnification, we can see the marks of the Vickers indentation, showing a typical example of a metal. These markings were made in Zurich, Switzerland, and you can see the swell marks of the material as it is being pushed out by the diamond indenter. The surface was not highly polished, so one has now the marking of the polishing equipment. There are still occlusions in the material. In the specimen I examined previously, one would get a combination of crystalline deposits and metals. This one now is more completely metal. This is the next stage after the previous one, number 6. And one can see now a much more precise evidence of a metal. We'll rotate the Wallenstein prism to bring out again. Here are structures. These are structures now that would not be seen normally except with the skill of a this type of development, these are areas of higher reflectivity. These are structures that are present here. One is seeing this by shifting a prism. I'm going to do it again. There it is. These bear investigation. There are things beyond that which are just looked at with ordinary light. Here we can see with the power of a television camera. This is the information that we should be looking at. Okay, we'll move on. This is the only specimen I have on number 6. We go to the previous specimens. We're now, this specimen is called number 4, same metal as the sample that turned to powder, dark, 3rd process. The silver is the 4th process, and the gold-silver is the 5th. The preliminary identification of this is copper, nickel, and silver. Silver solder, which is used for many forms of welding, is a combination of silver and nickel. Now, the specimen that I'm talking about is right here, and this is the specimen that we're talking about right here. The other lines that one see are the fracture lines from the embedment material and the cracking that took place. We'll go into polarizing the light. And now one gets a lot of the glare away, and one can see this specimen is dark, but there are, again, I call your attention to these lines, these vertical lines. Now we're going to look into that center part, that whitish area, and this line will increase the magnification and see. This contrast at around 50 diameters, we see these highly birefringent lines, flow process, and again, a series of vertical lines. We'll go to now polarized light and see what further detail. Here's some other areas. This is the boundary of this small particle. To give you an idea of dimension, we'll put a scale in to appreciate the dimension of this sample. These 2 lines here represent 1 millimeter, 1 thousandth, 1 millionth of a meter. And as one takes this away, one sees the specimen below. It's not very big. Again, these whitish areas around the specimen, showing that there was an interaction taking place between the plastic and the material. We'll go now to a higher magnification and polarized light. We're now looking at the specimen at 63x with a pole objective. The analyzer is out. One can see a small speck of the material. It's blackish in color, and because of the light now now we polarize the light. There's extinction position, and one can see there is a structure. As I rotate the analyzer slightly, it's tied in there. We'll move in different areas. Here's the edge. Here's a reaction from the edge of the specimen forming highly birefringent material. Again, these spots, which we see before, here is a complete distinct area. Pull the analyzer around. We're in the metal. see it. This is the boundary of the plastic. We're into the metal area here. This is number 4. This is the boundary in the plastic. Rotate the analyzer. We can bring it out. Here we are. There are 2 distinct areas here. These are the marks in the center of the picture again for Vickers hardness measurements. You can just see them. These were done in Switzerland. This will be reported on separately. We'll move on to the last specimen of these metals now. Very small, as one can see here with my finger, and we'll bring the specimen into view. This specimen was taken the first late summer last year, 1977 specimen of the metal from the spacecraft. This apparently was the one that disintegrated, and now we'll look at it. This is polarized light at higher magnification. The exciting thing about this specimen is you can see the various discrete agglomerates of metal, 2 distinct states, one here and another one in the more uniform polished background. These materials yet are not fused together, and one can see them even more critically by rotating the Nomarsky-Wollaston prism. Here's the edge of the specimen where it is molded in. One sees 2 distinct materials. Now we will go to polarized light to see if these materials are birefringent. Now under polarized light, one sees the distinct birefringent bits of material that are present against a matrix which is non-birefringent. I'll remove the analyzer. One can see this, and when one brings the analyzer in, one can see this, and has the polars crossed, one gets a birefringent area. One can be totally misled if one did an analysis of this in a gross way. One has to analyze now each of these areas. We see here the distinct birefringent areas with the polars crossed. Now I'll pull the analyzer out. One can see them, but much more distinctly that there is a birefringent area. This is number 1 sample, and as we go from 1, 4, 5, and 6, one sees a progression of diffusion of this birefringent material into the non-birefringent area. We must now analyze this material in this number 1 sample and move in the step-by-step evolution of this material into the final form that they have. It is very interesting to follow this, and one has to work now at this microscopic level. We are here now at about 160 diameters. These particles are very small, and one must deal with this on a microscopic basis. This is the end of the section now on the metals and metal samples that were given to me for examination. The next phase of this now will be the scanning electron microscopic examinations. We will look next at the specimens of crystals that were given for review and examination. Trine sample, which they say was from the planet Alcyon in the Pleiades chain. It is a very interestingly terminated specimen. The color you see here is accurately rendered. It is a golden yellow color, and as we move down the specimen, the final termination are in quartz-like crystal terminations. We'll polarize the light now to get better viewing of the termination. This gives a very nice view of the specimen. We move up. One can see now the various specimen's rather large, so one has to take it in pieces. Very interesting things are the growth patterns inside the crystal. Dealing with this crystal with sensitives, they say this is a very powerful healing crystal. It's a means of balancing the etheric body of an individual. On a separate videotape, I worked on focusing with the amethyst onto this crystal, and a cone of light could be seen on the Vidicon. I'll now focus on the specimen and see what we can do in modifying the energy pattern. This is the amethyst that I have. Again, my body vibrates, and this crystal starts to take on a bluish luminescence type of glow. Now comes a vibration at the tip of the crystal, which one can see change the raster lines. It comes in the breathing. Now the crystal is changing color. If one looks carefully at the tip, one can see a change in the color. This is the crystal I normally work with. Try to focus in. Left-hand lighting. Right. And I'll go into the overhead. Should try to bring out the inner details. Now we'll go into cesium iodide. There we're getting more detail. Anterior. Many, many hours of study required with this to explore, find out how to bring out this crystal. Remove the analyzer, and we will move on to the next crystal. On April the 20th, 1975, along with another lot of mineral specimens, a citrine crystal which you have just seen and an amethyst which is being shown now, crystal was brought from the planet Alcyon in the Pleiades and was delivered to the witness for his examination and analysis. Again he was warned that these elements are not stable in our physical chemical world of being, will have left the substance, and that he should look now for evidence of formation under different conditions of temperature, pressure, magnetics, gravity, axis of force, alignment of structure, etc. We're looking here, as far as I know, on a amethyst-tipped quartz specimen. The typical angles of quartz are evident. I'm showing it to you at this time. And now we'll move along the tip of the specimen to the base, and you can look at the various formations. This is a lower magnification. There's a panoply of colors. This is the base, white, from which this crystal grew, and then here is the end of the crystal. Polarize it so that we won't have as much glare. This is quite a common shaped crystal, typical of quartz. At the moment I see nothing unusual in this crystal except the beautiful amethyst color. Now we are under polarized light. Field is crossed. No birefringence. The light source is the quartz iodide. It will go into the more intense light source of the cesium iodide, and look for additional areas. We're dealing with three forms of illumination: two oblique sources, right and left, and an overhead bright field of the 250 watt cesium iodide. There is the opalescent area. It's a beautiful specimen which cannot be shown on the turning off the right and the left-hand light source and deal with the overhead light to try to bring out this beautiful orchid amethyst color. It's at the tip. It's remarkably beautiful. What I'm doing here is just removing the analyzer, letting the intense cesium iodide source burn in on this to bring out one face. And that's what we can do here. Now we'll move along the specimen. We're dealing with no lens in the microscope. I can see the growth lines. We'll go to a low power objective and take one more look at this and see what we can see. We're now at 63 diameters and moving along the crystal face. Very interesting to observe the various structures. Now we're at the edge of one boundary, and we come to the very edge of the crystal plane as she rotates downward. We'll bring this in a little better. Bring down Analyzer in. There it is. This is the raw specimen where, as one looks and sees the effect, we're going to go to higher light source, a little more dramatic. Take the analyzer out. And we go along. This concludes the optical examination under the microscope of the specimens, and the next series now will be devoted to the scanning electron microscopy.